Hello everyone, I am Bireshwar Roy. I am currently pursuing my third year PhD in the Department of Physics, Indian Institute of Science, Bangalore. In this course, I will be discussing some previous year GATE physics questions and try to solve them with proper explanations. So, this question was asked in the GATE physics paper 2021. This is a 2 marks MCQ type question. And this question was asked from the topic solid state physics, specifically from the chapter Semiconductor Physics. In the question it is given that in a semiconductor the ratio of the effective mass of hole to electron is 2:11 and the ratio of average relaxation time for hole to electron is 1:2. The ratio of the mobility of the hole to electron is option A 4:9, option B 4:11, option C 9:4 and option D is 11:4. So in order to solve this problem, we have to directly use the expression for mobility derived from the root theory of electron gas model. Now we know in a semiconductor there are two types of charge carriers. One is holes and other is electrons. Now holes are responsible for the conduction or the transport in the valence band and electrons are responsible for the conduction or transport in the conduction band. So we will apply the formula for mobility for both the electron and holes and we will take the ratio to find our desired answer. So let us go to the solution part. Now from the root theory of free electron gas model, we know the mobility of a charge carrier is given by mu equals to mod of E multiplied with tau divided by m star, where E is the electronic charge which is basically 1.6 into 10 to the power minus 19 coulomb. Tau is average relaxation time for the charged particle. It is also known as the mean scattering time, and m star is basically the effective mass of charged particle. Now the effective mass of a charged particle is defined from its actual mass. The effective mass is a quantity that is used to simplify band structure by modeling the behavior of a free particle with that mass. Now in the question it is given that the ratio of the scattering time for hole to electron is given by 1:2 and the effective mass ratio for the electron and hole is 11:2. We have to find the ratio of the mobility for holes to electron. So we will take the ratio of the mobilities for holes to electron. So after taking the ratio, we will get mu hole by mu electron equals to tau hole by tau electron multiplied with m star electron by m star hole. Now in the question it is given tau hole by tau electron is 1/2 and m star electron by m star hole is 11/2. So ultimately multiplying this we will get 11/4. So our result for mu hole is to mu electron is 11:4. So among the four options, the option D, that is 11:4, is the correct answer for our question. This question was asked in the GATE physics paper 2021. This is a MCQ type 1 mark question. This question is from the topic electromagnetic theory. The question is, consider a tiny current loop driven by a sinusoidal alternating current. If the surface integral of its time averaged Poynting vector is constant, then the magnitude of the time averaged magnetic field intensity at any arbitrary position r vector is proportional to option A 1 by r cube, option B 1 by r square, option C 1 by r, option D r. So we have to choose the correct option. Let us see the solution now. We have to consider a tiny current loop. Now a tiny current loop is basically analogous to a oscillating dipole. So we can consider a tiny current loop as a oscillating dipole whose Poynting vector is S vector equals to E cross H, where E vector is the electric field and H vector is the magnetic field intensity. It is also given the surface integral of its time average Poynting vector is constant. So the time average of S vector will be this, and which is basically time average of E cross H. Now, according to the question, the surface integral of the time averaged Poynting vector is constant. In the surface integral, this dA vector is the differential surface area vector. Now, if we represent this dA vector in the spherical polar coordinate, then it will become r square dr sine theta d theta and d phi. So, basically dA vector is proportional to r square. So, if the surface integral is constant, then it will lead to this time averaged Poynting vector will be proportional to 1 by r square, so that this surface integral will be constant. Now from this we can conclude our time averaged electric field vector will be proportional to 1 by r, and the time averaged magnetic field intensity will vary as 1 by r. If you remember the case of oscillating dipole, for an oscillating dipole, both the electric field and magnetic field varies as 1 by r. So among these four options, the option C is the correct answer, that is 1 by r. This question is from the GATE Physics paper 2021, and this is a 1 mark multiple select type question. This question was asked from the topic quantum statistics. The question is, for a finite system of fermions where the density of states increases with energy, the chemical potential, option A, decreases with temperature, option B, increases with temperature, option C, doesn't vary with temperature, and the last option, option D, corresponds to the energy where the occupation probability is 0.5. Now, as this is a multiple select type question, it is possible to have multiple options correct for this question. In order to solve this question, we have to have idea about three things. Number one, what is the distribution function or statistics applicable for fermionic system? Number two, what is the dimension of this fermionic system, that is one-dimensional or two-dimensional or three-dimensional, so that the dose, that is density of states, increases as a function of energy. And the last thing, of number three, for the particular dimension of this system, how does the chemical potential vary with the temperature? So using these three things, we'll solve this problem. Let us go to the solution part. We know fermions are particles with odd multiple of half integer, and they follow the Fermi Dirac statistics or Fermi Dirac distribution. The distribution function is given by 1 by e to the power e minus mu by kBt plus 1, where kB is the Boltzmann constant, T is the absolute temperature, E is the energy of the single particle state, and mu is the total chemical potential at temperature T. Now it is given in the question, we have to consider a finite system of fermions where dose, that is density of states, increases with energy. Now we know for the fermionic system, if it is one-dimensional, then dose varies as e to the power minus half, that is decreasing function of energy. And for two-dimensional fermionic system, it varies as e to the power 0, that is constant. And for three-dimensional fermionic system, the dose varies as e to the power half, so it is an increasing function. So for our case, the fermionic system is a three-dimensional system. The density of states versus energy plot for three-dimensional fermionic system looks like this. So that is, the density of states varies as e to the power half. Now, at finite temperature, the chemical potential is given by mu T equals to EF0 multiplied with 1 minus pi square by 12 into kb square T square by EF0 whole square plus some higher order terms, where EF0 is the chemical potential or the Fermi energy of this three-dimensional fermionic system at temperature equals to 0 Kelvin. Now, if you see this expression carefully, you will see the chemical potential will decrease as the temperature is increasing. So, among the four options, the option D, that is, as temperature increases, the chemical potential energy decreases, is the correct one. Now, we will verify for the other three options. We have already seen the distribution function for a fermionic system, which is also known as the occupation probability of the fermions, is given by 1 by e to the power e minus mu by kBt plus 1. If we plot this occupation probability as a function of energy, then it will be a step function for temperature equals to 0 Kelvin. It means all the fermions will be accommodated at the energy levels less than chemical potential for T is equal to 0 Kelvin. But for T not equal to 0, the plot will be a decreasing function of energy. Physically, this means some fermions will be thermally excited at the energy level higher than chemical potential. Now from the plot, you can clearly see the occupation probability for the energy equals to chemical potential will be half, that is 0.5. Also, you can directly calculate the occupation probability at E is equal to mu for T not equal to 0 Kelvin. That is 1 by, this part will have the value 1 and there is additional plus 1. So it will be 1 by 2, that is 0.5. So according to the solutions, option A and the option D are correct for this question. So for this multiple select question, option A and option D are the correct answers among the four options. This question was asked in the GATE Physics paper 2021. This is a numerical answer type 1-mark question, and this question was asked from the topic quantum statistics. The question is, three non-interacting bosonic particles of mass m each are in a one-dimensional infinite potential well of width a. The energy of the third excited state of the system is x multiplied with h cut squared pi square by m a square. Then the value of x in the integer form is, so we have to find the value of x for the third excited state of this system. In order to solve this problem, we need two important concepts, and they are: first, how are the energy levels located in one-dimensional infinite potential well of width a? And the second thing we have to know is that how are three bosonic particles will be arranged in the one-dimensional infinite potential well energy levels to have third excited state of this system. Now let us see the solution. If you have solved the problem for one-dimensional infinite well having width a in your basic quantum mechanics, then you know the energy spectrum for one-dimensional infinite well having width a is given by En equals to n square pi square h cut square divided by 2m a square, where n is the principal quantum number of this system. So En is the energy of the innate energy level of this potential well. H cut is the reduced Planck constant. M is the mass of the particle in that potential well. A is the width of the infinite potential well. Now, if you put n equals to 1, then the energy for the ground state, that is the first energy level, is given by pi square h cut square by 2m a square. So we can write the expression for the innate energy level is n square multiplied with E1. In the previous slide, we have already seen the energy spectrum of the one-dimensional infinite potential well. Now we'll see how can we accommodate the three bosons in the energy levels such that the system has the third excited state. We'll do it systematically. First, we'll find the ground state of the system, then first excited state, then second excited state, and finally we'll find the third excited state of this system. One important information regarding the boson particle is that there is no restriction on the bosons to be accommodated in a particular energy level. Hence, for the ground state, all the bosons will be accommodated in the ground state energy level, that is n is equal to 1. For first excited state, two bosons will be in the energy level n equals to 1 and remaining one boson will be accommodated in the energy level n equals to 2. For second excited state, one boson will be in the ground state, that is n is equal to 1, and the remaining two bosons will be in the energy level n equals to 2. And for third excited state, the arrangements of the three bosons will be like this. Two bosons will be in the energy level n equals to 1 and the other boson, that is the last boson, will be in the energy level n equals to 3. So this is the configuration of the bosons for third excited state. Hence, in third excited state, two bosons will be in n equals to 1 state and the other boson will be in the n equals to 3 state. Up to this, we already found the actual arrangement of three bosonic particles in the energy levels of one-dimensional potential well to achieve the third excited state of this system. Now we will calculate the total energy of the three bosonic system having third excited state. So in the third excited state, two bosons will be accommodated in the ground state energy level, that is first energy level, and the remaining one will be accommodated at the third energy level. So the total energy at the third excited state will be 2E1 plus E3. Now if we put the value of E1 and E3, it will be 2 multiplied by pi square h square by 2m a square plus, and for E3 it will be 3 square pi square h square by 2m a square. So that is 9 multiplied with pi square h square by 2m a square. If we add this, then it will be 1 plus 9 by 2 multiplied with pi square h square by m a square. After adding this, we will get 5.5 multiplied with pi square h square by m a square. So this 5.5 is your x. But we have to write the x in the integer form. So the nearest integer for 5.5 is this 6. So your x value will be 6 in the integer form. So for this numerical answer type question, the final answer is 6.